Hello, AP Physics 1 students. Let's get started on problem number 1 in the vectors and 2D kinematics concepts. So if you haven't already, go ahead and read the problem and just go ahead and do the vector diagram part of it. Now, just like it says, you don't have to actually measure anything, you don't have to measure any angles or measure any lengths, but when you do it, you want to try to draw everything somewhat to scale. So look at the relative sizes of the vectors and make sure they're proportional to each other when you draw them. And when you look at the angles, make sure they look, pretty correct. And here's our reference angle here that 0 degrees is positive x, 90 degrees positive y, 180 negative x, 270 negative y. And that's just going to give you your reference angles for when you're drawing them. So pause the video, go ahead and draw your vector diagram. Okay, so obviously I'm using the tools here on PowerPoint, but still I was sort of estimating how long things are and what sort of angles we're looking at here. And so here's what I did for vector A. I just drew something in the space there. Right, so that's going to represent the length of vector A, and it's at 0 degrees, so it's right along positive x. All right, now vector B, well, it's considerably shorter than vector A, right? Because that's what it says. And so I'm drawing it considerably shorter, and this looks like it's probably a 30-degree angle there. I don't know exactly if it's 30 degrees, but I know what 45 degrees looks like. That would be 45, like, directly up and to the right, and 30 degrees is just smaller than that. That's all I'm really looking for. But notice, of course, I'm using the tail to head method. That's the only way you should be doing vector addition. So if that's not what you did, if instead, for example, if you put vector B over here, maybe like tail to tail with vector A, well, then pause the video and start over. You're not going to learn anything by just copying the vector diagram you see here on the screen. You have to do it correctly on your own first. And then if you have to make corrections, that's fine. Okay, so then from here, we're going to do vector C, which is, in this case, 120 degrees, which is 30 degrees away from 90, so 90 would be straight to the top of the page, and 30 degrees beyond that is 120. Notice I put a little sort of like crosshairs here just to give a sense of like the coordinate axes, like the middle of that, like 0 degrees, 90 degrees, that would be 120. Now, how long is vector C? Well, it's considerably longer than vector B, and right, you have to draw it really long to look like this. Does yours have to look exactly like mine? It doesn't look exactly like it, but yours should look generally like this. And then from there, tail to head, vector D points to 270, which is straight to the bottom of the page. And, maybe try to make it maybe about half of vector C. Obviously, it's not exactly, right? But you're basically trying to draw it somewhat to scale. So if yours doesn't look exactly like mine, that's fine, but generally, it should look like this. Of course, the vector diagram is not complete until you draw the resultant, and since we're doing the tail to head method, the resultant is also drawn from tail to head, from start to finish. And it's a vector, and it's got an arrow. All these are vectors, right? They all have to have arrowheads. This doesn't make any sense if you don't draw the arrowheads on them. That's not a vector diagram. I draw the resultant in a different color, as we've seen in other videos, but if you don't have different colors, you can certainly just use like a thicker vector. But the point is you should draw the resultant different from the originals because it's an either-or situation. Either an object moves along vector A, vector B, vector C, vector D, and ends up there, or it goes in a straight line path from start to finish. So it is an either-or sort of situation. And here I'm calling the resultant vector R, although these are all displacements, so it could be a total displacement. Okay, so that's what our vector diagram looks like. That's the first part. Now we have to talk about what do we do next? How do you actually solve this vector problem to find, for example, the magnitude and direction of the resultant? We're not actually going to find it. We're just going to talk strategically how to do it. So the whole idea is, in the end, you want to make the resultant vector the hypotenuse of its own right triangle. Because if it's the hypotenuse of its own right triangle, then it's very easy. You just put the legs together using Pythagorean theorem to find the hypotenuse, and you can use some inverse whatever you want to do to find the angle. So that's generally our goal. Now, since these other vectors are at random angles, they don't make any sort of nice geometric pattern here. The most generic thing you could do is resolve everything into components. Once you resolve everything into x and y components, well, then we have a structure to move forward. So we take vector b and we resolve it into an x and a y component. And if this were, north, south, east, west, you can call this east, you can call this north, but we're just talking generically. So x and y. If it's, up, down, left, right, you can call this the horizontal, you can call this the vertical. We just don't know what the orientation is. So I'm just calling it generically x and y. When I draw the components, I draw them as dashed lines because they're imaginary. We're imagining taking vector b and replacing it with its components. So we're building a right triangle around vector b, which, we also have to show direction for that. Vector b points to the top right corner of the page, and so we have a component pointing to the right and a component pointing to the top, and so we have arrowheads on our components. We're going to do the same thing for vector c. Now, it doesn't really matter where you put these components. For example, if you take the vector c and put its components here and here, that's fine. Just Now that's sort of inside the whole diagram here. It might make it kind of cluttered. So I chose to put the components of vector C sort of more on the outside. That's a personal choice. Totally doesn't matter how you actually do it. This is, I think, makes it a little less cluttered than otherwise. But there's still the x component pointing, in the horizontal direction on the paper, and there's the y component pointing in the vertical direction on the paper. Plus, this is also good because it does incorporate a 30-degree angle there, which is nice and easy to visualize. Okay. And then it is traditional to scribble out the original vectors. That's one more visual representation that you're taking the original vector and replacing it with its components. All right, so first step, if you're listing your steps, first step is to resolve all vectors into x and y components, or vertical and horizontal components, whatever it is. But the point is resolve everything into components. Now, we don't have to do this with vector A because it's already pointing only along the x direction. We don't have to do it with vector D because it's already pointing along the y direction. So the first step, again, is resolve everything into components. And then, of course, you would mathematically calculate the values of these. We're just not taking that step right now. We're just talking more strategically. What do you want to do next? Well, once we have everything in x and y components, the whole point is to put like components together, right? So if a person would walk along vector A and then along vector B sub x, then later walk along vector C sub x, that's going to get the overall x direction of their displacement. You can do the same thing for the y's. The whole point is we want to try to get the components of vector r, just how much vector r is in the x direction, how much vector r is in the y direction. So again, the whole point is to try to do this, try to build a right triangle around vector r. So r in the x direction is just the combination of all the x components. R in the y direction is the combination of all the y components of the original vectors. Okay, so again, first step, resolve everything into components. Second step, build a right triangle around the resultant vector, because that really is our end goal. So this makes a very nice, easy last step. Now, once again, mathematically, you have some numbers here. You can put these together, a and bx and cx. Now, notice there's no actual dx, because d is not in the x direction at all. Just that's this particular example, so I still left it here. In similar fashion, in the y direction, a doesn't have a y component, so this would be 0. It's not pointing along y at all, but I still left it in here to make it more generic. But vector a in the x direction is pointing, to the right, and vector b in the x direction is pointing to the right, and vector c in the x direction, that's pointing to the left. And so you can't just mathematically just add the numbers together. What do we really have to do, since they're pointing in opposite directions? Well, what we always do, we have to assign a positive direction. So I just arbitrarily said to the right is positive and to the top of the page is positive. You don't have to do that. You can really assign anything that makes sense to you. These just seem to be convenient. Okay, so first step, resolve everything into components. Second step, build a right triangle out of the resultant vector. Third step, set a positive direction. And the fourth step, actually go ahead and combine these mathematically, incorporating the positive and negative signs. All right, so once you do that, you'll have the magnitude of vector Rx, magnitude of vector Ry, and then I just took the whole thing and separated out here. That's an optional step. It's up to you if you want to do that. I just think, again, it's a little bit cluttered in here, a little bit easier to see. And from here, it just becomes a very basic vector addition problem because we made a right triangle. We do have to get magnitude and direction. We always want to think about which angle we're going to be finding, whether it's the lower left or the upper right. And we do have rules for this. It's not arbitrary. It's not up to you. The rules are we always pick the angle near the start of the vector diagram. And so this is the start of the vector diagram, right? That's where this whole process started. So we're going to be finding that angle theta in there. We're using Pythagorean theorem, of course, to find the magnitude of this. And I left it, very generic. Obviously, these could be displacements, these could be velocities, whatever it is. And then here's the angle theta we're looking for. Now you can choose any of the inverse trig functions you like. I happen to prefer doing inverse tangents just because we already found Rx and Ry by combining all these components here, but then when we found the magnitude of the hypotenuse, very likely you had to round something along the way, and this is just a little bit easier, sometimes these are more round numbers and like that. You'll get very similar answers regardless, but I tend to do it as inverse tangent. There's not a rule, you can obviously do whatever you want, but this is just the routine I tend to follow. So obviously it's going to be inverse tangent of the opposite with r sub y over the adjacent, which is r sub x. This notation right here, it literally says absolute value. That is a vector notation. When you put absolute value bars around a vector symbol, it says take the magnitude of it, which is literally what we're doing here by doing Pythagorean theorem. Okay, so these are the generic steps. First step, resolve everything into x and y components. Second step is you're imagining building a right triangle around the resultant vector so you can visualize its components. Third step, setting a positive direction. Fourth step, mathematically combining all the like components, all the x components together, all the y components together. And then the fourth step, or the last step, is, whatever order you want to go in here, actually finding the angle using your inverse, whatever trigonometric function you choose, and finding the hypotenuse here, the magnitude, by doing Pythagorean theorem. And again, this process can be applied to any sort of vectors, whether they're displacements or velocities or forces or accelerations, whatever it is. This is a very generic strategy for doing any sort of vector problem, no matter how complicated it gets.